So in this video, we're going to talk about how to understand transformations when they're expressed with function notation. So remember that function notation is used to represent an equation that is a function. So remember, we can use any letter of the alphabet to represent a function, right? So we can call a function f of x, g of x, or any other letter that you want. So you'll start to see that using function notation is a quick, condensed way of describing transformations, and especially now that we've learned about composite functions and evaluating functions at a specific value. So what we're going to do is we're going to start off with our parent function f of x, okay? And then we'll call our transformed function g of x. And what we can do is we can add in values called a, b, h, or k, and those are going to create transformations. So a is going to have an effect. It's going to be a vertical stretch if the absolute value of a is greater than 1, vertical compression if the absolute value of a is between 0 and 1, and a reflection over the x-axis when a is less than 0. B is going to be our horizontal change, right? Because anything that's inside where our input is going to be a horizontal change. So it's going to be a stretch if the absolute value of B is between 0 and 1, a compression if the absolute value of B is greater than 1, and a reflection over the y-axis if B is less than 0. So, and also H is going to create a horizontal change because once again, you see that B and H are affecting the input of this function. So it's going to be a shift left when we have something like x plus H. And it's kind of the opposite of what we think is going to be, right? And we'll talk about why when we look at some graphs. It's going to be a shift right when we have x minus h. And then k is going to be what's affecting the output, right? Anything on the outside is going to be affecting the output of f of x. So that's why it's going to be a vertical change. So it's going to be a shift up when we have plus k and then a shift down when we have minus k. So here is a summary of this just in chart form, right? So if we have f of x transformed to a times f of x, you can see it's a vertical stretch or compression or a reflection. If we have f of x transformed to f of b times x, it's going to be a horizontal stretch or compression or a reflection over the y-axis. If it's f of x becomes f of x minus h, we have a shift right when h is greater than 0, so that's going to look like an x minus h. And then it's a shift left when its h is less than 0, so it's going to be an x plus h. And then we have f of x transformed to f of x plus k, and it's going to shift up when k is greater than 0, and then down when k is less than 0. So let's look at some examples with the absolute value parent function. So in this case, when we talk about f of x, that's going to be f of x equals the absolute value of x, okay? So that's the nice thing about using function notation to describe transformations is that f of x can be anything that we define it to be, okay? So in this video, we're going to be talking about f of x being the absolute value of x. So now let's try this example. Given f of x equals the absolute value of x, let's describe how the graph of g of x equals f of x plus 1 has been transformed from f of x. So notice what happens here is we have a transformation in the input. So we have a value of h that's changing our function. Well, it's written in terms of x minus h. So what we can do is we can rewrite this as f of x minus negative 1, okay? So that means our h is equal to negative 1. Well, when h is negative 1, it's going to be shifted to the left 1 unit. Okay, so it's going to be shifted left 1 unit. And like I said before, you do want to graph in Desmos to verify these transformations. So to graph it in Desmos, you're going to need to see what the absolute value equation is going to look like. Well, remember what we studied with function notation. I'm going to take this x plus 1 and I'm going to plug it into this absolute value equation. So that means my transform function g of x is going to be the absolute value of x plus 1. And you can go ahead and graph this in Desmos and see what the graph actually looks like, and you can see that it has been shifted to the left 1 unit. Okay, so now let's try this example. Given f of x equals the absolute value of x, let's describe how the graph of g of x equals negative 2 f of x has been transformed from f of x. Okay, so the change here is that we have a value of a, right? Well, this a is actually going to have two effects because a is equal to negative 2. Well, since the absolute value of a is going to be equal to 2, and that's bigger than 1, we're going to have a vertical stretch, right? That's going to be one change. Another change that we're going to have is because negative 2 is less than 0, right? So that's going to be a reflection over the x-axis. Okay, so we actually have two effects because this a has a value of negative 2. And so remember, you want to graph this in Desmos to see what it looks like on this transformation, right? So what this is telling me is it's saying, well, take f of x and multiply it by negative 2, okay? So I'm going to go to this function and I'm going to rewrite that as g of x equals negative 2 times the absolute value of x, okay? So you can graph that in Desmos and see how the graph has been transformed. Well, now let's try this example. It says describe using function notation and by writing an equation how the function f of x is transformed when it's reflected over the x-axis and shifted up 5 units. Well, reflected over the x-axis means we need an a value that's less than 0, right? So since a is less than 0, we don't have any other transformations from a, right? We don't have a stretch or a compression. So the way to do that is just to say a equals -1, okay? Because -1 is less than 0, but then also we won't have any of those stretch or compressions going on. Another change we have is shifted up 5 units, okay? So up 5 means that k equals +5. So if I was going to write this using a function rule, I would say that g of x equals negative f of x and then +5, right? So that would be the transformed function. So I can also write this because we're talking about absolute values, right? Remember, f of x is equal to the absolute value of x. So I can write this as negative absolute value of x and then +5. Right? So that's going to be our transformed function. So now you can go ahead and pause the video and try doing this one on your own. So here it says, how is the function transformed when it's shifted left 5 units and vertically stretched by a factor of 2? Okay, left 5 units. So left 5 means my h is going to be -5, right? So when I plug that in, well, that's going to be like x minus -5, which that's just going to turn into a plus, so that's going to be x plus 5, right? So that's what's going to change my input of the function. Vertically stretched by a factor of 2 means that a equals 2. So if I write this as a function rule, that means that g of x equals 2 times f of x plus 5. Okay, so that's, function notation. If I want to write this using the absolute value function, like f of x equals the absolute value of x, that means I'm just going to plug it in. So that means my g of x is going to equal 2 times the absolute value of x plus 5. Okay, you can graph that in Desmos and see that it is in fact transformed that way. Okay, so function notation can help us describe transformations in a concise manner. So it's something that I want you all to get used to as we start learning about transformations.